Alright guys, we are moving on to section 3, which is all about ways to transfer thermal energy. And in this section we are going to talk about the 3 methods of transfer, which are conduction, convection, and radiation. And if we look at a pot on a gas burning stove, we really have all 3 ways of thermal energy transfer. So let's take a look here at conduction. Again, going back to the kinetic theory, remember that particles are always in random motion, and thermal energy can be transferred from particle to particle when they collide. And this is what conduction is. It's that transfer of energy through collision. And again, heat is what we call that transfer of energy from the higher temperature to the lower temperature. Big thing here, and hopefully you guys have experience with this, is heat, or metals are good conductors of heat. They transfer energy very quickly. If you've ever roasted marshmallows on an open campfire and you've accidentally touched the metal part of the fork, the roasting stick, you will know how hot that gets very quickly. There's wood on the ends for a reason. We'll get to why that is here in a little bit. But when we talk about conductors, because all materials, solids, liquids, gases, plasma, are all made of particles that can collide, conduction can happen in all states of matter. However, which one do you think would conduct heat the fastest? Solid, liquid, or gas? If you answered solids, you are correct. The particles are much tighter packed together, so they are going to collide with each other much more frequently. Thinking back to your journal question from last week in the analogy of the stadium, those of you that answered the solids are like the fans in the stands, okay, how tightly packed in they are. Where if you had some people on the field, much more liquid, you're not going to collide quite as often. So conductors, okay, that collision, so if we have the most collisions in a solid, they're the best conductors. You can still, though, again, have conduction in liquids and solids. It just does not happen as rapidly. Second method of convection, okay, liquids and gases only can transfer thermal energy by convection. Solids cannot. The reason why is because convection is the transfer of thermal energy in a fluid from place to place. Key word here is fluid. Okay. And solids are not fluid. Liquids are fluid. They can move around. Gases are fluid. They can move around. So convection can only happen in liquids and gases. Convection current, one of the things you had to do on your pre-reading today was to draw a convection current. Okay, convection currents occur because of the density differences between warmer and cooler fluids. Hot water versus cold water. A warm air mass versus a colder air mass. Warm air, or warm water in this case, at the bottom of the beaker, okay, is less dense than the colder water at top. So let's draw a little picture of what's going on here. We've got our beaker. Okay, we have our flame. Okay, so the water in here, oops, blue for my water. Okay, starts being heated up at the bottom. So this warm water at the bottom becomes less dense and it wants to rise to the top. As it rises to the top, it forces this colder water down to the bottom. And then the bottom gets warmer and becomes less dense and rises back up, which forces the cooler, more dense back down to the bottom. And you get this constant cycle of the rising of the warm, less dense, and the sinking of the cooler, more dense. Okay, this also happens in an atmosphere with air masses. If we've got our Earth, okay, again, Mrs. Falkavage is by no means an artist. Okay, that's North and South America, in case you can't figure that out. Okay. Huh?
I'll agree she's not an artist, that's for sure.
That was Mr. Falk making fun of my picture of North and South America. Now my feelings are hurt, and I don't know if I can continue with this lesson.
You'll be okay.
All right, so we've got our cold air masses at the poles, and you've got this warm air masses at the equator. These warm air masses circulate air towards the poles, and the cold air masses circulate the cold air towards the equator. And again, you get this circulation of air masses in a convection current. And looking at these pictures, if any of you want to have me autograph a screenshot of these right now, I would be happy to later.
Worth nothing.
Moving on to the final method of thermal energy transfer, which is radiation. Radiation is the most important method of thermal energy transfer, and it is the form of energy transfer using electromagnetic waves. And the reason why you feel warm when you are standing by a campfire is mostly because of radiation. Hopefully it's not conduction. If you don't know, don't touch the fire. Okay, most likely you are not standing on top of the fire or above it, so you're not getting those convection currents. You're off to the side and you're feeling that warmth through the transfer of energy in the form of electromagnetic waves. Radiation can pass through solids, liquids, and gases, but it's most important in gases. Gases are not dense at all, so it's very easy for those electromagnetic waves to pass through them. Even more important, going back to my first comment about radiation being the most important form of thermal energy for us, that's because radiation is how we get our heat from the sun. Remember, space by definition is the absence of matter. So you can't have particles colliding, so you don't get conduction. Convection's not going to work because there's no particles to be moving around and rising and sinking because of density differences. So the only way to get thermal energy from the sun is through radiation. Okay, so how does this work? When radiant waves strike a material, one of two things happens. It's either absorbed or it's reflected. Okay, some gets transferred through the material, but for the most part, absorbed and reflected. If you've ever stood outside on a hot summer day, you are going to be privy to this next stuff. Light-colored materials reflect more than dark-colored materials. If you go outside in the summer in a white shirt versus a black shirt, you are going to feel this very difference. That white shirt is going to have the electromagnetic waves bounce off of it, where the black shirt is going to absorb those electromagnetic waves, and therefore the thermal energy is going to increase, and you're going to feel that heat much more intensely than if you are wearing light colors. In fact, you could wear a long sleeve white shirt and feel cooler than in a black tank top. So, flow of thermal energy. It can be a good thing and it can be a bad thing. In the winter, we want to keep that thermal energy close to our bodies. We don't want to lose our thermal energy. So how do we keep warm in the winter? When we take a hot pan out of the oven, we want that thermal energy to stay on that pan. We don't want it to pass to our hands. In each of those cases, to be able to keep warm in the winter or to take a hot pan out of the oven, we are using a material that's going to insulate and reduce the flow of thermal energy. Our coats are designed to keep thermal energy close to our body, slow the flow of thermal energy, and an oven mitt is designed to reduce the flow of thermal energy so it doesn't pass from the pan to our hand. Okay, these things are called thermal insulators. And a thermal insulator is any material in which thermal energy is slowed down. Whether it's through conduction, convection, or radiation, it's slowing down that transfer. Okay. At the beginning of this chapter, the beginning of this section, we talked about metals being good conductors. Therefore, they would make bad insulators. Remember, we talked about solids being good conductors. So they're the worst insulators. But gases, okay, that collision doesn't happen very much, so they actually make really good insulators. But we have to know how to use gases to maximize their effect, because if I just had a big open space in between the outside of my house and my drywall, I'm going to feel that cold pass through. So what is it about the insulation that helps my house stay warm? How is it that there's gas in there trapped in between these interwoven fibers that helps keep the thermal energy from transferring? And what it is there's pockets of air. If you've ever looked closely at fiberglass insulation, you can see these interwoven fibers and all these little tiny pockets of air that keep convection currents from forming. If you've ever worn a down coat, those feathers, okay, form little pockets of air all over the place to keep convection currents from occurring. Okay, it's why birds are able to stay warm in the winter, because their feathers create those pockets of air. Tomorrow's lab is going to be very important that you come prepared. It's 20 minutes of straight data collection. Read the lab very carefully. Look at the pictures. We're going to have the lab mostly set up for you, so you should be able to plug in your probeware and change the settings and get things recorded so that you can be successful tomorrow. Make sure you have your entry ticket done. Do it now. You have plenty of time. Get your lab notebook set up. Again, you have plenty of time. If you have any questions, let me know, and be ready again for lab tomorrow.